Over the last few modules, we have journeyed to the black hole Cygnus X1 to explore the black hole binary system and see the wondrous sights outside the event horizon. We then dove inside to explore the mysteries hidden behind the event horizon. We learned that the boundary between the inside and outside of a black hole is actually rather fuzzy once we include the laws of quantum physics. In fact, quantum mechanics suggests that black holes aren't actually black, and they can actually leak out their contents and eventually disappear. Scientists today have different levels of understanding of the phenomena associated with black holes. First of all, there is excellent evidence that black holes do exist. The fundamental characteristics of a black hole, such as the location and properties of the event horizon, the innermost stable circular orbit, spatial curvature, and time dilation, are well understood and are no longer controversial. We see excellent evidence of jets, accretion disks, and many features of accretion in many black hole systems. However, we do not yet have a full understanding of all of these processes. Thankfully, we have lots of telescopes observing these systems, and we are building a very good understanding of these structures, which we will begin to explore more in the next few modules. Crossing through the event horizon, we enter a region where it is predicted to be impossible for light or anything else to escape. So we have no observational confirmation of the mathematical theories describing the interior. However, as long as we don't include quantum physics, it is possible to write out all of the equations describing the inside of a black hole, including the singularity. Quantum mechanics, the science of the very small, and how it applies to black holes, is still a big open question. Since quantum mechanics is normally only important for describing small objects, the introduction of the ideas of quantum physics mainly only affects tiny black holes. For the smallest black holes, we cannot be certain whether particles are inside or outside of the event horizon. This leads to the prediction of Hawking radiation, which culminates in the evaporation of a black hole. A related problem is that of information. Is it truly destroyed when it enters a black hole? This is a question many astronomical theorists are still pondering. However, we should remember that quantum mechanics is probably also important if we want to understand the singularity of all black holes, whether or not they are small. Addressing questions such as the properties of the singularity, information loss, and the final result of black hole evaporation will require physics that has not yet been uncovered, a quantum theory of gravity. There are only hints of what a quantum theory of gravity might look like, but full details are beyond our present understanding. Now that we have explored some really big unknowns, it's time to look more closely at all the really cool phenomena that we can see when we point our telescopes at black holes.